Dropout does this seemingly crazy thing of randomly knocking out units in your network. Why does it work so well as a regularizer? Let's gain some better intuition. In the previous video, I gave this intuition that Dropout randomly knocks out units in your network, so it's as if on every iteration you're working with a smaller neural network, and so using a smaller neural network seems like it should have a regularizing effect. Here's a second intuition, which is, let's look at it from the perspective of a single unit, right? Let's say this one. Now, for this unit to do its job, it has 4 inputs and it needs to generate some meaningful output. Now, with Dropout, the inputs can get randomly eliminated. Sometimes those 2 units would get eliminated, sometimes a different unit would get eliminated. So what this means is that this unit, which I'm circling in purple, it can't rely on any one feature, because any one feature could go away at random, or any one of its own inputs could go away at random. So in particular, it'll be reluctant to put all of its bets on, say, just this input, right? The weights will be reluctant to put too much weight on any one input because it could go away. So this unit will be more motivated to spread out its weights and give you a little bit of weight to each of the 4 inputs to this unit. And by spreading out the weights, this will tend to have an effect of shrinking the squared norm of the weights. And so, similar to what we saw with L2 regularization, the effect of implementing Dropout is that it shrinks the weights, and similar to L2 regularization, it helps to prevent overfitting. But it turns out that Dropout can formally be shown to be an adaptive form of L2 regularization, but the L2 penalty on different weights are different, depending on the size of the activations being multiplied into that weight. But to summarize, it is possible to show that Dropout has a similar effect to L2 regularization. Only the L2 regularization applied to different weights can be a little bit different and even more adaptive to the scale of different inputs. One more detail for when you're implementing Dropout. Here's a network where you have 3 input features. This is 7 hidden units here, 7, 3, 2, 1. So one of the parameters we had to choose was the keep prop, right, which is a chance of keeping a unit in each layer. So it is also feasible to vary keep prop by layer. So for the first layer, your matrix W1 will be 7 by 3. Your second weight matrix will be 7 by 7. W3 will be 3 by 7, and so on. And so W2 is actually the biggest weight matrix, right? Because they're actually the largest set of parameters will be in W2, which is 7 by 7. So to reduce overfitting of that matrix, maybe for this layer, I guess this is layer 2, you might have a key prop that's relatively low, say 0.5. Whereas for different layers where you might worry less about overfitting, you could have a higher key prop. Maybe this is 0.7, maybe this is 0.7. And then for layers where you don't worry about overfitting at all, you can have a key prop of 1.0, right? So, for clarity, these are numbers I'm drawing on the purple boxes. These could be different key props for different layers. Notice that the key prop of 1.0 means that you're keeping every unit, and so you're really not using Dropout for that layer. But for layers where you're more worried about overfitting, really the layers with a lot of parameters, you could set key prop to be smaller to apply a more powerful form of Dropout. It's kind of like cranking up the regularization parameter lambda for L2 regularization, where you try to regularize some layers more than others. And technically, you can also apply Dropout to the input layer, where you can have some chance of, just axing out one or more of the input features. Although in practice, usually don't do that often. And so a key prop of 1.0 is quite common for the input layer. You might also use a very high value, maybe 0.9, but it's much less likely that, you want to eliminate half of the input features. So usually key prop, if you apply it at all, will be a number close to 1, if you even apply Dropout at all to the input layer. So just to summarize, if you're more worried about some layers overfitting than others, you can set a lower key prop for some layers than others. The downside is this gives you even more hyperparameters to search for using cross-validation. One other alternative might be to have some layers where you apply Dropout and some layers where you don't apply Dropout, and then just have one hyperparameter, which is a key prop for the layers for which you do apply Dropout. And before we wrap up, just a couple implementational tips. Many of the first successful implementations of dropouts were to computer vision. So in computer vision, the input size is so big. You're inputting all these pixels that you almost never have enough data. And so dropout is very frequently used in computer vision. And there are some computer vision researchers that pretty much always use it, almost as a default. But really, the thing to remember is that dropout is a regularization technique. It helps prevent overfitting. And so unless my algorithm is overfitting, I wouldn't actually bother to use dropout. So it's used somewhat less often in other application areas. It's just if computer vision, you usually just don't have enough data, so you're almost always overfitting, which is why there tend to be some computer vision researchers that just swear by dropout. But the intuition doesn't always generalize, I think, to other disciplines. One big downside of dropout is that the cost function j is no longer well defined. On every iteration, you're randomly, killing off a bunch of nodes. And so if you're double checking the performance of gradient descent, it's actually harder to double check that, right? You have a well-defined cost function j that is going downhill on every iteration, because the cost function j that you're optimizing is actually less well-defined, or is certainly hard to calculate. So you lose this debugging tool to be able to plot a graph like this. So what I usually do is turn off dropout, or if you will, set key prop equals 1, and then run my code and make sure that it is monotonically decreasing j, and then turn on dropout and hope that, I didn't introduce a bug into my code during dropout, because you need other ways, I guess, but not plotting these figures to make sure that your code is working, the gradient descent is working, even with dropout. So with that, there's still a few more regularization techniques that are worth your knowing. Let's talk about a few more such techniques in the next video.